Hello, everyone. In this video, we will analyze and design an efficient algorithm for finding Fibonacci numbers using dynamic programming. Fibonacci numbers is a sequence of numbers begins with 0 and 1. All the subsequent numbers are the previous two numbers add together. For example, this 13 is derived from 5 plus 8. 55 is derived from 21 plus 34. We're going to write a program to compute the Fibonacci numbers at a given index. So the index 11, the number is 89. We use recursion to find the Fibonacci numbers as Fib at index 0 is 0, at index 1 is 1. At this index, Fib index is the previous two add together. We compute the previous two, Fib index minus 1 plus Fib index minus 2. This is very natural using recursion to define the Fibonacci numbers, and we can write the code using recursion now. Using recursion, this is the recursive method. Fib index 0, return 0, index 1, return 1, else we can return Fib index minus 1 plus Fib index minus 2. Now let's look at the time complexity. We already know it when we study recursion using Fibonacci number as example. It is very inefficient. If you have this number is 10, it's going to be very slow. If it's 20, it's even slower. It's very visible. And why? Because it's an exponential time algorithm. So look at this complexity. For this index n, this is time complexity. So we need t n minus 1, the time for computing this Fibonacci number at index n minus 1, and the t n minus 2, the time for computing the Fibonacci number at the index n minus 2. Now, if you derive this, and you're going to see it is order of 2's n. Therefore, the recursive Fibonacci number method takes order of 2's n time. It is very inefficient. If you run the code using index 20, you're going to see this is exceeding the allowed time. So this is 20. I'm going to have this is 50. The program takes too long. It runs out of the allowed CPU time. We need to design a better algorithm. What can we do is to use this observation. So we can introduce three variables, F0, F1, and F2. F2 is F0 plus F1. Now we continue now to the next one is now we're going to shift everything now, assign F1 to F0 F2 to F1. And now you compute the next one is the new F0 plus the new F1. That is the simple idea. And let's write the code here is we have F0 initially is 0, F1 initially is 1, F2 is initially is 1, that is F0 plus F1. And look at this n. If n is 0, return F0, n is 1, return F1, n is 2, return F2. Now, for this index I is 3, we're going to assign F1 to F0, F2 to F1. Now you get new F2 is the new F0 plus new F1. And now start over again, do the same thing. So now you update every time in this loop, you update F0, F1, and then F2. So after all this is done, you have reached to the index n, return F2. And this is really fast. So now if you run this code using this 100, and you get the result right away. So this is the number, and for the index. Here, the index is 100, and the Fibonacci number is right here. So let's see what's the time complexity. And that is the time complexity. It's a linear time. So you can see this is the only one for loop, and this is the n. So it's order of n time. It's a linear time. Now the technique we use in this program, it's called a dynamic programming. Dynamic programming is to solve subproblems, then combine the solutions of subproblems to obtain an overall solution. This naturally leads to a recursive solution. However, it would be inefficient to use recursion because the subproblems overlap. That's why the recursive solution for this problem is so inefficient. You have to do a lot of redundant work. The key idea behind dynamic program is to solve each subproblem only once and storing the results for subproblems for later use to avoid redundant computing. So we have all the previous two numbers all stored all the time, update it, and get a new number. So when you compute the Fibonacci number at new location, you don't have to go back to recompute everything. So previous two numbers are already in place. And that's the key for dynamic programming to design the efficient algorithm. That is all for this video. Thank you for watching. See you on the next video.